So in the last couple of talks we took a plane region, a two-dimensional plane region, and revolved it around an axis, forming a solid, three-dimensional solid, and we did it in such a way with this volume of revolution that we came out with figures that not only were pleasing to the eye, but were probably practical, something that you could manufacture and use in real life. And there was two ways we did this. One, when the axis of revolution was right up against the two-dimensional plane region, we used a disk method. We derived that formula to get the volume, and then when there was space in between the axis and the plane region, then we came up with another formula, and that was called the washer method. So today we're going to just look at one other method that makes similarly nice looking practical objects that they would manufacture in some manufacturing plant. And this is called solids with known cross sections. So I think the way I'm going to do it is to start with an example and then kind of build a formula from that example. So let the base of a solid be the first quadrant plane region bounded by this parabola and the x-axis and the y-axis. So we've got the x and y-axes, and then we have this parabola that when x is 0 is 1, and when x is 2, you get 0. So you've got something that looks like this. So if I was graphing it, I would do that. Now, on this particular one, I'm going to try to show you why you can get something that looks relatively nice. What we're going to do is we're going to make this as our base, and then building in a third dimension out from the board, we're going to make cross sections that are squares. So if we were to take a cross section of this three-dimensional solid, there'd be a big square right here, there'd be a medium-sized square, and then the squares would keep getting smaller. To do the math, you don't need to have a picture. In fact, sometimes it gets in your way, but for once I'll try to show you why it might look okay. So if we had a third axis, like the z-axis coming out of here, where this is kind of representing coming out of the board, we're going to have these cross sections that are squares. My wife is an artist, and she showed me how to do this, otherwise I would never be able to. So you get a figure that looks something like this. So basically, this big square right here would be coming out. And when you have all these squares together, diminishing in size, it makes a nice rounded surface. So I'm just hoping you can see that this would make something of value. So anyway, but I'm not going to ever do this when I'm actually trying to find the volume. What am I going to do instead is I'm going to divide this up, just like we did before, into n sections. I'm going to call this x sub 0, this might be a in general, and this is b, and this is x sub n. In this case, a is going to be 0 and b is going to be 2. But then we're going to take a kth section from xk minus 1 to xk and pick a value somewhere in there, c sub k, and that's going to be our height, and then we're going to use delta x sub k to be our width. So what we're going to do is then make this square, in this case it'll be a square as our cross section coming out of here. And what we get, if you just looked at this one section, if you pull it out of there, you're going to get this square, but then it's going to have a little bit of width. And the width is going to be this same delta x sub k that we've had before. So if I just pull this out of here, I get a box. And this is something that I know how to get the volume of. So if I took the area of this face, this square, and then multiplied it by the third dimension, which is delta x, well, actually it's going to be delta c sub k, because we're using that to get our height. So altogether, the volume of that box is going to be A of c sub k, because that's going to be our x value, and the width is going to be delta x sub k. Actually, we call this delta x sub k, this width. So that's the volume of one box, and then all we're going to do is add them up. But because we have this little bit of air, like we always do, we're going to make them really skinny by taking the limit as n approaches infinity, or as the norm of the partition approaches 0. And what we get, again, we have the variable is x. This is just a function of an x variable in here. So this is an infinite Riemann sum, or a definite integral. So we could write this, the integral from a to b of a of x dx. And we've got a formula. And the nice thing about this formula, if the cross sections were not squares, but something else, maybe the cross sections could be a equilateral triangle coming out of the board. Like that, it would be done the same way. Because to get the volume of this three-dimensional figure made from a equilateral triangle, you're still going to take the area of this base, the two-dimensional, and multiply by that third dimension, which is always going to end up to be this delta x sub k. So we've got a formula. We've derived it. And I think I've made the argument enough that you agree that if I made my rectangles on the side, then it would be the integral from c to d of a of y dy. The area of the cross sections would depend on the y value and not the x value. Here, depending on the x value, you get a different cross-sectional area. So, these are our formulas. So let's see if it works on this problem. We're going to go, the volume is the integral from a to b. In this case, it's 0 to 2. And a of x, since this is a square, the formula for a square is the side squared. So all we have to do is figure out what the side is going to be. Well, the side is just this distance right here. And it's the y value on this curve, so it's just 1 minus x squared over 2. And we've got our setup. So now we square it out, 1 minus, and then you're going to get, if you had 1 minus x squared over 2 times 1 minus x squared over 2, you get a minus x squared over 2, and then a minus x squared over 2, so you just get a minus, oh, I'm sorry, it's x squared over 4 that we've got up here. So it's 1 minus x squared over 4 squared. So you have 1 times 1 is 1, and then you'll have plus or minus x squared over 2 and plus x to the 4th over 16. If you take that integral from 0 to 2, you get x minus, and then this becomes x cubed over 6 plus x to the 5th over 80. Luckily, we're only going from 0 to 2. So we get 2 minus 4/3 plus 32/80, which, if you put 16 in there, you get 2/5. And 0 gives you 0. So basically, you get 2/3 plus 2/5. And the common denominator would be 15. So 10 plus 6, 16/15. So that would be the volume of this three-dimensional solid. So let's see if we can then apply this to other problems. The base of a solid is the region between one arch of y equals the square root of the sine of x, because it's going to keep going all the way along the x-axis. But we're only going to look at one arch. So when sine of 0 is 0, the sine of pi is 0, and then you're going to get an arc like that. So perpendicular to the x-axis. So we know which way to make our rectangle, dx. And since this is a cross-section problem, we've already got a formula. It's right here. So I can say right away, this is usually the first thing I write on my papers, I write a of x dx, because I know that's the formula. No matter what the cross-section is, and in this case I'm going from 0 to pi to add up these cross-sections. So it all comes down to what is the cross-section and what's the area formula for that cross-section. Well, in this case, they're equilateral triangles. So you have to decide, do you remember the formula for an equilateral triangle? If not, you can always just go back and draw an equilateral triangle and know it's 1/2 the base times the height. Well, in an equilateral triangle, all the sides are the same. So this would be a 60-degree angle, and that's a 30-degree angle. And this is s over 2 on this side. And we know in a 30, 60, 90 triangle, the ratio is 1 to 2 to the square root of 3. So the height would be s over 2 times the square root of 3. So the base is s, and the height is s over 2 times the square root of 3. So altogether, what do you get? You get s squared, but then times the square root of 3 over 4. So if you didn't remember that, you can always rederive it. And that's the formula for an equilateral triangle's area. So that's what I have to put in here. And I can put the square root of 3 over 4 out front, and then just put the side squared. Well, what is the side? The side is from here to here. It's the square root of the sine of x. And that works out really nicely because the square root squared is just the sine of x. We still have that square root of 3 over 4 out front. The antiderivative of the sine is minus the cosine of x. So we get minus a minus 1, or 1, and the minus the cosine of 0 is minus 1. So altogether we get 2 times the square root of 3 over 4, or the square root of 3 over 2 cubic units for what you get when you use this as a base, and then we have equilateral triangles coming out into the third dimension. Okay, so let's try 2 more of these. And I think that'll pretty much solidify how you do these. Now, the thing I made different of this one, the base of the solid is the first quadrant region between this parabola, y equals x squared, and the x-axis from 0 to 3. This this time though, the cross sections are going to be perpendicular to the y-axis. So this time, the cross sections are going to come out perpendicular to the y-axis, so we make our rectangle in this direction. We have to go dy. But no problem, we just go the integral of a of y dy. And we have to be careful though, because we're not going from 0 to 3, we're going in the y direction. So this point up here is 3, 9, so we're going from 0 to 9. And what are the cross sections? They're semicircles. So this is the diameter of the semicircle, and then it's coming out. Different size semicircles are going to be coming out of the board, forming this three-dimensional solid. So what is the formula for a semicircle? It's 1/2 pi r squared. Now, here's another place where you have to be a little careful because it's r squared, it's not the diameter squared. This distance right here is the diameter. So we want to make sure we divide by 2. And what is this distance right here? Well, we measure in that distance from the y-axis. So from here to here is 3, and from here to here is the x value on this curve. So we have to resolve that and get x equals, it's plus or minus the square root of y, but we're only looking at the plus side over here. So that means this distance right here is the square root of y. And this distance here is 3, so what we have is 3 minus the square root of y. And that would be your setup. I don't want to take all your time on this, but just to show you what I would do, the first thing I would do is get rid of that fraction. 2 times 2 is 4. I could take this right out front and make it pi over 8. And then you just have to square the top, which would be 3 minus the square root of y times 3 minus the square root of y. You would have 9 minus 2 square roots of y, and then plus y. And I think we could work this out further, but we've done a lot of practice with the fundamental theorem of calculus, so I'll leave that one to you. Okay, so let's do one more. The base of a solid is the circular region. So here's a circle. X squared plus y squared is 4. So that's our base. The cross sections are perpendicular to the x-axis, so I can make those right now. And I know it's going to be dx, and I know this is a cross-section problem, so right away I can say the integral of a of x dx. And I'm going to go from -2 to 2. Now, first of all, I always like to make my job a little bit easier. I can see in a circle that from the y-axis over to the right and the y-axis over to the left, they're both the same semicircle and they're going to have the same cross sections coming out. So I could just go twice the integral from 0 to 2. Just get the volume for this side and double it. So what are our cross sections this time? They're right triangles. So what's the formula for a right triangle? It's 1/2 the base times the height. And it says the short leg is in the base of this solid. So this is the short leg right here. So what is that distance? Well, you measure from the y-axis up. So if you solve this, you get y squared equals 4 minus x squared, or y equals plus or minus the square root of 4 minus x squared. So this is plus the square root of 4 minus x squared, and this is minus. So the whole distance is going to be 2 times the square root of 4 minus x squared. Now, how about the other leg in this right triangle? They say it's 5 times as long as the shorter one. So all I have to do is make it 5 times as big as this one, which makes it 10 times the square root of 4 minus x squared. And at first look, this one looks pretty hard to do, but then you say, oh, cross out that. You can take the 10 out front. You have 20. And the square root squared is just 4 minus x squared. And it turns out to be not so bad. We might as well finish this one. So 4x minus x cubed over 3 from 0 to 2. We get nothing from 0, but 2 is going to give us 8 minus 8 thirds. Well, 24 thirds minus 8 thirds is 16 thirds times 20. And so we get 320 thirds cubic units, whatever they happen to be. So anyway, there's 4 examples using different types of cross sections. And I think you see, once you've got it set up, if we had a different type of cross section, all we have to do is change this. Everything else stays the same. So, I don't know. I just would like to take another minute or two just to kind of explain what we've done so far this year and how magical it is. We started out with trying to find the slope along the curve, but we know we needed 2 points to get a slope, and we wanted to find the instantaneous slope at 1 point. So what we did is we let the rise over the run be the slope between the 2 points, but then we let the run approach 0. Well, you can't divide by 0, so we used this limit. We took the limit as this run, which we call h, approach 0. And automatically, magically, we were able to we turned 2 points into 1 point. I'm trying to show you how magical math is, how you can turn 2 points into 1 point. Now, what have we done recently? Now we've been trying to find the area in between some kind of figure that's not a normal geometric figure that we know a formula for the area. And what we did is take rectangles and added them up. But we always had this little bit of air. So what did we do? We took and made them really, really skinny by making an infinite number. We took the limit as the number of rectangles approached 0. And what did we do? We turned rectangles into straight lines. No air. Isn't that magical? So far we've turned 2 dots into 1 dot. We've turned rectangles into straight lines. And then without elaborating too much, what did we do when we did the disk method? When we did the disk method, we took these right circular cylinders and made them so skinny that they really just became circles. And there was no air. So we turned cylinders into circles. So don't let anybody tell you that math is boring. It's very magical. So have some good wizardry the rest of your day.